once again coming to you not quite live from One Take Studios, where we are kind of picking up with our last conversation here. All right, I think I bumped my camera. There we go, I like that better. Okay, so with this, we had talked previously about an introduction to statistical tests, so we are continuing that conversation today with testing the mean mu, and this has a couple directions that it can and will go. So by way of a brief review of what happened last time, all right, we started off by taking our problem and saying, all right, what is our null hypothesis, what is our alternate hypothesis, and what is our alpha, what is our level of significance? So kind of organizing our thoughts and our data. Then we said, well, let's figure out what the sample test statistic is. You may not have been paying attention to those words last time, so watch what they are this time. I'm intentionally leaving a space because there's a couple things I want to put there. And then we said, all right, well, let's take our information and let's sketch it and see what this looks like if we put it all together. Is it left-tailed? Is it right-tailed? What's going on? And then we compute the p-value because we said that the p-value compared to focus, there we go. The p-value compared to the level of significance helps us to determine what's going to happen with this. So we would reject the null hypothesis in favor of the alternate if the p-value is less than the level of significance. We are saying if this is going to be smaller than alpha, that means that the likelihood of this happening accidentally is really slim. And so if it's really slim that it would happen accidentally, there's a good chance that this is off. This is wrong. We should reject it and look someplace else. All right, and then we put that all together in context. There are two directions that two things I want to put here. There's a couple of things that you can list for the sample test statistic, but usually what I'm looking for are one of these two things. Either squeeze, there we go. All right. If we are testing for mu, when we know what sigma is known. This is what we looked at last time. This is the z-score. This is how we find it. And we got to say that n is greater than or equal to 30, or we know that the distribution is normal, and we can run it like this. Compared to, there's a ton of similarity between this and some of our conversations about confidence intervals, because we can also test when sigma is unknown. So the difference between known and unknown, any chance you remember something there? What is at the back of the brain? Oh, maybe something about a t-score perhaps? Dun dun dun. Yes, ladies and gentlemen, if we do not know sigma, then we go with a t-distribution instead of a standard normal distribution. And the student's t-distribution is kind of like normal, but it has thicker tails and there's a few differences, so it is a little bit different. This was the thing that had degrees of freedom with n-1, and we would calculate the t-score very similarly to the way that we would calculate the z-score. It's still x bar minus mu, but because we do not know sigma, we are doing s over the square root of n. For this to be something that is predictable and reliable, we still would want to know that n is greater than or equal to 30, or know that it's approximately normal, because again, this is not the exact same thing as normal. It's slightly different. Okay, so what I'd like to do then is hopefully that you've watched both of these videos, because I'm going to do a comparison here. I am not starting from scratch with this, okay? You are going to find this ton similar to our previous example in our last video when we were talking about the introduction. We still have Loretta. Her mean time for running 2 miles is still 27 minutes. Her last 5 run times are still 26, 24, 25, 23, and 27 minutes. So since a lot of these are smaller than 27, we suspect that maybe we can say that her run time is decreased, that it's no longer 27. Possibly. Notice I made 2 changes here, really. One is that this time we're going to use a level of significance at 5%. In the last video, we used 1%. And last time I had something in the margins here that I left out on purpose this time. The last time we said, hey, we know that our sigma, our standard deviation, is going to be 2.1. This time, you will see there is no mention of sigma anywhere. Known versus unknown. We are in unknown category right now. Because we do not know sigma, either you will see no mention of sigma whatsoever, or you may actually see one of these problems with S in it. So if you see S instead of sigma, that's also a good indication that you are in unknown territory. I did not put S in this problem because, quite frankly, I have a data set, and guess where S comes from? Yeah, that would be the standard deviation of just these 5 runs. So I'm intentionally running this a little bit different from last time so that we can see differences and notice what's happening with this. So if we start with some things that we know, we've got a lot of similarity there as well. We know that our null hypothesis is still that it's a 27-minute run. And we suspect, based on our sample data, that mu has actually decreased, but we don't know that for sure, but we suspect it's less than 27, which means it is still going to be left-tailed. By the way, right-tailed and two-tailed are strikingly similar as long as you are using the calculator. The difference would be if you're using the tables, this gets a little bit weird because tables tend to be left-tailed. So calculators are our friends. Oof, tables. Tables are sad. I get it. They had to exist once upon a time. They don't have to exist anymore, though. All right, so we're talking left-tailed with this. Other things that we know. Oh, you know what? I'm going to let this kind of go at the moment. I'm going to call this good for right now. Oh, I do want to mention one more thing. Ooh, let's throw this in there. We have to know that our level of significance is 5%, because again, that's going to be important later on as well. All right, so we got those guys. I'm going to go to the calculator and show us a different direction with the calculator at the moment. And I have a new document here. Actually, I don't want a calculation screen. I'm going to throw in a new page here, so Control add a page to my document. And I'm going to go with lists and spreadsheets for this. And I'm going to put in just my most recent data runs. So the first one was 26 minutes, followed by 24, followed by 25, and 23, and 27. So these were her 5 most recent runs. All right, so you've got all those numbers in a column. What I'm going to do is this. Again, everything fun and exciting is in the menu. We are still talking about statistics. We want to do a test, all right, stat test, but choose wisely, okay? We've got a z-test last time because we knew sigma. You have to say, I don't know sigma this time. I need to go with a t-test instead. And because we actually have data, I'm going to leave this as data instead of statistics and tell it, all right, that's fine. It's going to ask us what was the null. So again, the 0 is the null hypothesis. That was a 27-minute thing. Notice how little information we need to put in here, really, because it has the list of data so it can run a bunch of calculations on its own. The list that we gave it is in column A. The frequency is 1. And we are saying with this that we suspect that it is actually less than 27. And putting the results in column B is great. I'm going to click this too because this is sort of fascinating. It'll do a drawing for us. It makes it a little bit hard to read the screen because it'll be a split screen, but I think it's worth looking at. All right, so we shall tell it okay, and here is life. Here is what we have. We see a pretty picture. Ooh, we see the shading down here in the corner for this one. We see, right at the top, it tells us what this was for t and what this was for the p-value. So your t-score, kind of like your z-score, we can kind of put this together and take a peek. So, things that we know. I don't know about you, I'm taking a moment to sketch this. It looks really super duper tall, so maybe I'll make my sketch a little bit taller than normal. We got that going in place. We are saying that 27, again, would have been at the middle of the peak for raw data. And we are looking at, again, this has an x-bar of 25, so 25 would be the raw data value for our current location. If we compare that, though, to something that is more standardized, that means that 0 would be at the center, and that's what we see here, is we see this actually put up compared to a student's t-distribution, 0 here. And if you look, this is just to the right of -3, which makes sense because this has a t-score of -2.8. So -2.8 would be the t-score, -2.8. All right, so I'm going to go ahead and I'm going to click out of this for a moment. I may come back to it. We shall see where to go. There it is, right there. Okay, so among other things here, I want to jump back over to this guy real quick. I left this space. We said that we are looking for the sample test statistic, and really one of the telltale ones is going to be either the z-score or the t-score. There are other sample test statistics, but to my mind, these are the ones that are really telltale for deciding what's going on with this. So again, this is 27. We still have the x-bar, and if I put this here, the x-bar for this is still 25, the same as yesterday, but those are the raw data values. So when we put this in a student's t-distribution, instead of having 27 at the middle, we have 0 at the middle, and this gives me a t-score of -2.8. So t is negative 2.8. Again, we're saying this is right here, and this is right here. Oh, guess what I forgot to write down? Yep, I forgot to write that down. So again, here's my shading. What did I leave out that's important? Do you know? Yeah, I forgot to write down the p-value. Let's jump back over to the other screen then, just for a moment. P-value is what? Was 0.0237. 0237. Okay. All right. And let's see. I'm going to go with... shoot. Any chance you want to humor me? Are you willing to humor me? This is One Take Studios. We can handle this, right? I want to change something. I do. I want to change something. All right, I'm going to go back to my other screen again. There we go. You know what I want to do? Just for better contrast for yesterday? I want to call this 1% again. I think. Do I? No. You know what? No, leave it 5. Leave it 5. We're going to call it 5. There we go. I mean that. Okay. All right, so we have our p-value at 0.0237, so a little over 2%. We have alpha, level of significance, at 5%. We know we're looking at this. Again, our decision for this is truly based on the comparison between this and this right here. Is this likely? Not super likely, but the question is this terribly unlikely? Is this p-value ridiculously small? Small enough to the point that we would say, you know what, this is tiny enough that it is significant for us to say 27 is probably a bad idea. Again, what do we do to put this together? We compare the two. We say, all right, I've got a p-value of 0.0237, and I know that my level of significance is 5%. So 2 plus some percent compared to 5%, that is less. This is my decision factor right here, all right? This tells me everything that I need to know. That's a star, that's a star, there we go. This right here, I don't get to make my own decisions, they're based on this. Because we are at 5% this time, because we are at 5%, my p-value is smaller than 5%. Because this is 5%, this is larger than yesterday's example or the day before, whenever you watch that, this is what we would consider to be ridiculously small. What does this mean for statements? This means that today I would say the data is significant. Significant. All right, last time this was going to be larger than the 1%, and we said the data was not significant. This time, because it's smaller, because it's tiny, tiny means significant. The data is significant enough to reject Loretta's mean run time of squish 27 minutes. So this time, because it is significant, we are rejecting. Last time it was not significant, so we did not reject. This time it is significant, so we are rejecting this thing. Notice the difference. There is a difference. Wording is important. It is meaningful. So what are we saying? Have we proved that her mean time is not 27 minutes? No, we said that the data that we've collected here, this sample, is significant enough because this probability is smaller than 5%. So it is significant enough to say, you know what? I'm going to reject the 27 minutes. And I can probably say this is going to be smaller. I don't know what my true mean is, but it's going to be less than 27. So I can say I'm going to favor a value that's less than 27 by rejecting the 27 minutes. Okay, again, practice, play with it, ask questions. If you are just saying, tell me what to do and I do it, you are not thinking. You will not retain this. You will not understand it. It will be a bad day for you. So do your best to understand it. Think about what's happening. Piece it together. Pay attention to the details. All of it. Okay? All right. Have fun, people.